Okay, well, we are going to quickly wrap up this current lesson, and then the only other thing I have to take care of today is going to be the quiz, so you'll actually have probably a solid half hour, if the other two classes are any indication, to go ahead and finish that up. You got your homework today. That'll be due on Tuesday. Tomorrow when you walk in, we'll have a focus activity, and then I'm just going to give you the rest of the period to go ahead and work on that. We'll probably go ahead and do a couple of problems together, and then that's due on Tuesday, as I said. But next Thursday, that's the big item. What is that? That's the exam. So the exam will cover sequences, both arithmetic and geometric. Okay, so I didn't put any vectors on there. This is the last time we'll have an assessment, well, for right now, with vectors. So definitely want to start taking a look at that. Do your best on the assignment. Come in with questions if you have any. I think that's it. So let's go ahead and finish up the notes. So the last problem here talks about converging or diverging sequences. And what was the difference? What did those mean? Okay, so Christian says the same number. Okay, so if the sequence goes towards a specific number? Okay. There you go. Okay, so if you're looking at your sequence, and what we did was use a characteristic from rational functions to kind of help us with this, but if the pattern you notice in your sequence has it going towards a specific number, if it approaches one number, meaning the limit exists, we're going to say that the sequence converges. If it doesn't approach one specific number, then there's no limit. We go ahead and say that it converges. And we have these three rational functions here. Now, we use the degree in order to help us out, but what is it about the degree that gives us these three different cases? Because basically we're talking about a horizontal or a slant asymptote. So what's one case we could have? How could the degrees relate to each other? They could be the same. Okay, so what happens if the degrees of the numerator and denominator are the same? You divide the leading coefficient, so that would be your horizontal asymptote. Okay, what if the degree of the numerator is larger than the degree of the denominator? Is that a horizontal or slant? Okay, so I heard slant, I heard horizontal. Oh, that's what we said. Mhm. So you're absolutely right. Okay. So if the numerator's degree is larger, yes, that's going to be a slant asymptote. And you probably use synthetic or long division in order to figure that one out. And what happens if the denominator's degree is larger? That's zero. It's just the x-axis. Okay, y equals 0 has a horizontal asymptote. So let's take a look at these problems here. A says 3n over n plus 1. What do we notice about the degrees of the numerator and denominator? Are they the same or different? The, the degrees are the same. So that tells me I would do what? We would just divide the leading coefficients. So 3 divided by 1, this would have a horizontal asymptote. So as far as our limit statement, we could go ahead and say the limit as n approaches infinity of 3n over n plus 1 is 3. Okay. So if we were looking at this graphically, just to kind of give you an idea real fast, we would have, 3 right here. And if you think way back to when we did this, we never went ahead and put the middle of it because we refer to it as the ends. We said it only as it approached positive or negative infinity. And we'd have to do a little more analyzing to tell, but whether the graph, the branch approaches the asymptote from above or below, okay, let's say it looks like that, as that value of x, or n in this case, gets larger, yeah, you're going to get closer and closer to 3. Even though you won't touch it, we say that's the limit. So if you think about n just being the x value and the sequence itself being the corresponding y value, okay, so this can be representative of a sequence. All right, so what would you say about this one? Does it converge or diverge? It converges. There you go, because it goes to a specific number. So I'm going to say it converges. There we go. Let's try B. 5n squared over n cubed plus 1. So it looks like the denominator's degree is larger this time. So what does that mean? Okay, it's 0. All right, so we have another horizontal asymptote. So I can say the limit as n approaches infinity of my function, 5n squared over n cubed plus 1 is equal to 0. Because it does approach a specific number, we say it what? Converges. Okay, there is a limit. And in fact, you could say it converges to 0. Okay, there we go. And then we've got our last one here, n cubed plus 2 divided by n squared plus n. All right. So it looks like the numerator's degree is larger this time. We said that was a slant asymptote. So we'll find it in just a second, but let's kind of think about this. Let me go ahead and write out my statement. The limit as n approaches infinity, it just becomes increasingly large, of n cubed plus 2 over n squared plus n. Okay. Well, what do you think it's going to be? We have a slant asymptote. It is going to be infinity. Well, we're going to come to find out the slope of our slant asymptote is going to turn out to be positive. So as n gets larger, okay, even though we're approaching that linear function, y is just going to continue to increase the value of it without bound. Yeah. So it is going to be positive infinity. It's just going to keep growing. Is it possible for the limit to approach negative infinity? Yeah. Now, in either case, whether it's positive or negative, what would I say here? It diverges. This does not approach a specific number. And there we go. And just for practice, we really don't need to do it, but it's fun. So n squared plus n, let's actually go ahead and perform the division. So I want to take my divisor, divide it into my dividend. But when I write this out, there's something I need to do. What am I referring to? There we go. We need those zero coefficients because we need it in decreasing order of the variables. So if there's a missing term, see, it goes from n cubed to the constant. So we need to put in 0 n squared plus 0 n, and then we can put in the plus 2. Okay. Now, I already had the one worked out yesterday, but let's kind of walk through the process. How does this work? Okay, so we've got to figure out one term, something to put here that's going to give me an n cubed right there. We always want to match up those leading terms. So n cubed times what is n squared, excuse me, times what is an n cubed? Just n. Now, once I figure out that first term, I want to distribute it across my divisor. So n and n squared will give me n cubed. N times n will give me n squared. And see, that's why we had to go ahead and plug in those zero coefficient terms, because we want to make sure our like terms match up. Now, what do we do after we multiply? Distribute and negative. He's absolutely right, because we're going to subtract. That's why yesterday I had those in a different color, because I wanted you to see what was actually happening there. So these two terms that you always match up should become opposites. 0 n squared minus n squared is a negative n squared. And then we're going to bring down the plus 0 n, and we'll go ahead and do it one more time. So n squared times what is a negative n squared? Okay, negative 1. So minus 1. And then we'll distribute again. So there's the negative n squared, negative 1 times n, negative n. And what happens when you subtract a negative? It becomes positive. Okay. So those once again cancel. 0n plus n is just n. Bring down the 2. And then you could continue, but your slant asymptote, it's going to be a linear function because the degree of the numerator was just 1 degree larger than the denominators. So really, if you were to use, I don't remember, when we talked about this, did I show you reduced form? Did I actually show you the analysis where we plug in infinity and see what happens? I honestly don't remember. Okay, now there is a form where when you plug in infinity, these are just going to disappear anyway. Really all you're interested in is the mx plus b. Okay, so in this case, n minus 1. And we are correct, we ended up with a positive slope. So, did he go ahead and talk about the reduced form? Okay, I didn't think that I did it this year.
Your remainder doesn't really matter.
Oh, did he? Okay, good, good, good. Okay. So let's go ahead and put the negative 1 there, positive slope. Probably going to look something like that. Blue. Okay. All right. Listen. Here. And here, again, pretend that the x is just this n that we're using here. So as n just gets larger and larger, however the branch is going to approach the slant asymptote, whether it's from above or below, in either case, as n gets bigger, that corresponding y value is just going to continue to grow as it approaches that linear function. That's why we went ahead and said the infinity. Okay, so good. Any questions? Anybody having any trouble with sequences, formulas, anything of that nature? Okay, then that wraps up that lesson. Okay, when's the homework due? Tuesday. So we will have the majority of our time tomorrow to work on it. We do have that focus activity. All right, so